what it was that Hess was trying to tell us, those many years ago? What's the basic foundation of what Hess's law is about? What does it actually mean? Anyone give me just sort of like a brief explanation about what it is?
I kind of look at it as like a way to manipulate certain equations to fit the total equation of like a reaction, I guess.
Okay, but when you think about that, yeah, that's one way of putting it. But when you think about basically a chemical reaction, there's lots of different ways to get to it. I mean, we haven't really, most of the reactions we've been dealing with have been really straightforward. Like, this one reactant together with this one other reactant, they come together and make something. And in chemistry in the real world, it's not as simple as that, because a lot of reactions are really complicated, and they're more than one step. We've been dealing with single step reactions where two things come together and they make a new thing, and that's the end of it. But really, most chemical reactions, particularly when we think about just the reactions that take place in our body. I mean, I'm a biochemist by training, and when you eat food, basically it gets broken down into carbon dioxide and water and energy. If we were to write that out, it would just be like, sugar plus equals CO2 and H2O. But I think we know enough that that's actually not what happens. The end result is that, but it's about a 40-step process to get there, where you take out little bits of energy from each small step. But if you added all those steps together, you get sugar plus oxygen gives you CO2, H2O, and water. And Hess's law is telling us you can figure out, if you added up all the energies from all those small steps together, they would equal the energy from the large step. That's basically what it is. There's going to be intermediates in those reactions. There's going to be things that are produced in some of those small step reactions that then get consumed in another reaction, and that's what happens in your body. There's lots and lots of intermediates that come and go, that like they form and then they're gone. They form and then they're gone. They're produced and then consumed. And the same thing happens with these equations. So basically what it is we're trying to do is take these equations, which are basically intermediate reactions. They're sub-steps. They're steps along the way of getting to where we need to go. We need to figure out how to add them, subtract them, how to manipulate them in order to figure out how much energy goes into the complete process and how much energy comes out. So yeah, so let's have a look at the first one. So I've sort of broken these down by what is the reaction we want, which is on the top, and what reactions go into making that, which are on the bottom. The ones with the delta H next to them. So the first reaction, we don't know how much energy goes into that reaction. We don't know if it's an exothermic reaction or an endothermic reaction. We have no idea. But we do know that the two reactions below it are part of the overall reaction. And so we know that one of them looks like it's exothermic and one of them is endothermic. Who can tell me which one is endothermic and which one's exothermic? Which is the exothermic reaction here?
-42439 kilojoules.
Right. That's the second reaction. It's exothermic. So when something's negative, that means that after the reaction's over, the amount of energy has decreased, and that energy has been lost in the form of heat, and that's how much heat has been lost. So if we did that reaction we were holding onto the reaction container, it would feel warm because the energy has gone down in the system. Remember, when we're dealing with thermochemistry, there's the system and then there's surroundings. And the system is the actual reaction itself, and the surroundings is everything else. So that negative is energy going from the reaction to the surroundings. Third reaction is endothermic. That's the amount of energy that would go into the reaction. And so if we were holding on, to that reaction vessel while that was occurring, would it feel warm or would it feel cold? What do you think?
Would it be warmer?
You think it would get warmer than it was?
We're talking about the second
The
reaction, or the third reaction.
the third one. Yeah, the third one.
Okay.
So that's an
Yeah, I would think it would
reaction.
be warmer.
Okay. Anybody else? Remember, it's endothermic. So which direction is the energy going? Is it going into the reaction or is it coming out of the reaction? So it's plus 3438 kilojoules plus. So is that energy going into the reaction or is it coming out of the reaction?
Into?
Into. Where's it coming from?
Outside?
Right. So the energy is coming from the outside into the reaction. So would that feel warm or feel cold?
It would feel warm, right? Because it's gaining heat, essentially.
It's gaining heat, but where's the heat coming from?
Oh, the outside, right?
Right. So would it feel cold or warm?
Cold.
Cold. That's right. It would feel cold. That heat's got to come from somewhere.
Right.
And that, so basically, what's weird to think about is, like, you know, as a reaction gains heat, it's the outside, it's the surroundings that have to lose it. And so that would feel cold because the heat would be basically coming from your hands and the surrounding the reaction vessel. And so that would feel colder because the heat would be going in rather than coming out. So our question here is for the first reaction, PCl5 is our reactant, and then it gives us PCl3 and chlorine gas. Is that going to be an exothermic or an endothermic reaction? We don't know. So what's the first step in doing these sort of reactions? What's like basically the first thing we want to do? Or what's the first thing you guys do when you look, other than just panic and cry? What's the first thing you want to do when you're doing these sorts of reactions?
Formal equation.
Try a little more.
What so what's the first step?
From what I see, I can see that the first equation have P4 on the reactant side and the second equation have P4 at the product side. So which means that we can eliminate it.
But is that the first thing you want to do? What's the very first thing you want to do? Yes, it would.
Look for the substance that we want to eliminate from the equation, system of equation.
Okay.
So we can see that the equation we want doesn't have P4. So
Right,
we might
so-
want to do something about it.
Yes, we will, but I would think it's not the first thing you want to do. Though you have very, very smartly seen that P4 as a solid is going to be an intermediate because it is not present in our overall reaction on top. It's not there. And so we know that P4 is going to be produced in one reaction and it's going to be consumed in another one, and then it will be gone. So there won't be any left. But the first thing I'd like to do when I'm doing these equations is find where are my reactants and where are my products. So I look at the first thing I want to, whoops, let me go back. get something to draw with. The first thing I want to do is look for my reactants. So here's PCl5, which is what would we call that? Anyone remember what we would call that? What's the name of that?
Phosphate pentachloride.
Phosphorus pentachloride. Yep, phosphorus pentachloride. So we need to have that as a reactant. And so what we're going to do is we're going to look for it as a reactant or a product. So you can see that the third reaction here has it as a reactant as well. Let me annotate again. Yeah, so we have it here as a reactant. So we're going to leave that for now because all we know right now is that we won't have to flip that. We may have to divide it or multiply it or something, but we won't have to flip it. It's in the right direction. So next we want to look for the products. So I've got two products. I've got PCl3 and I've got chlorine gas, and I want to find those. So where am I going to find those?
So you see, I guess the 4PCl3 is on the product side for the second reaction.
Right, so I've got PCl, which is phosphorus trichloride, is a product in my second reaction, so that's good. And I've got chlorine gas as both a product and a reactant. I've got it as a reactant in number 2, and I've got it as a product in number 3. So what I want to do basically is figure out, I'm probably going to have to do something with one of these reactions to get everything to balance out, right? So what am I going to need to do to number 2? I'm going to need to do something to that in order to get everything to balance out properly.
We divide number 2 by 4.
Okay, so if I divide number 2 by 4,
We get 1 mole of PCl5 phosphorus pentachloride, and then 1/4 mole of P4, and 2.5 moles of chlorine chloride. And then if we divide the first equation by 4, we get.
But we can't do that. We can't divide the first one. What we want to end up with.
Dun dun dun.
We want to end up with?
Yes, this first one.
Oh, wait.
That's our targeted goal, right? That's what we're trying to aim for.
That's the target.
Yeah.
What are your labels for the equation? Is it 1, 2, 3 in order?
Yeah, so we want to finish with 1. So this first one, we want to finish with that. So we need to manipulate the second one. This is number 2, and this is number 3. We need to manipulate those two.
Oh, I divided both number 2 and number 3 by 4.
Divide them both by 4.
Yeah.
Okay. Let's try that. So that would give us 1. That would give us 1/4 P4 plus what is it? 1.5. Oops.
Wouldn't it be 3/2 for the chloride?
Yes.
Chloride? 3/2.
Chlorine. Chlorine, not chloride.
Chlorine.
Oh, yeah, chloride. Did I say chlorine?
You did.
I think it's
I did. Okay.
Did. We all heard you.
Ah, I see.
Right. So that would give us 3/2 chlorines and 1 PCl3. So the bottom one would be PCl5. Oops, goes to 1/4 P4 plus 10 divided by 4 would be 5/2, right? 2.5
Yeah, that's right.
chlorines. All right, so let's add those together. So I have got so 1/4 P4 on both sides. Get rid of that. I've got 3/4 chlorine on one side, and I've got 5/2 on the other. So what's my net number of chlorines?
1
On which side?
on the product side.
Yes. So get rid of that, and I'm left with 1. And I've got PCl3 on this side as a product, and I got 1 PCl5 on that side as a reactant. So when we add them all together, you get PCl5 goes to PCl3 plus Cl2. That works. So what do we do with the energies? Now remember, these are our energies. So we've managed to balance the equation and we've come out with the target. But the whole point of this is to get the energies right. So what do we do to the energy for experiment number 2?
I divided it by 4.
Okay. So what's your delta H for this now?
Negative 609.75.
609.75.
And the same with equation 3. 859.5.
That's a positive, right?
Oh, positive, yeah.
805.5.
5. 859?
Oh, sorry. Yeah, I messed that up.
It's okay.
That was the result of dividing it by 4, right?
859.5.
Dividing both of them by 4.
Oh.
Yeah. Yeah, so whatever you do to the equation, you have to, whatever you do to the reaction, you do exactly the same thing to your heat. So what's my total?
200, positive 249.75 kilojoules.
250?
249.75.
249.75 kilojoules. Yeah.
Is that right, guys?
Yeah.
That looks right to
Yeah.
me. Very good.
I can verify that.
Yeah, you guys did a great job on that one. I also have the answers somewhere, but I really didn't print them out. But that definitely looks right. I mean, I'm obviously I'm going to post all these a little bit later. But yeah, that's excellent.
Mm-hmm.
That one's a little tricky. That one's hard when you see you've got reactants on both sides. Kind of, then it's hard to know which one you're gonna deal with. But yeah, it also shows that just take it step by step. You can always go back and change one or change the other. But yeah, I also get confused when you have to have things by half. Obviously, 3 halves and 5 halves and that sort of thing. But you're going to see that in these sort of questions. All right, yeah, excellent job. So let's go to the next one. Right, so this one's got threes. This one's a little trickier. So we want to finish with basically the reverse of a combustion reaction. It's a combustion reaction in reverse, because we've got water and CO2 as reactants, and we're getting out of it acetylene and oxygen. So it's basically the burning of acetylene in reverse. So I pretty much think we know what side this reaction should have. You think this will be an endothermic or an exothermic reaction? This reaction number 1 here. If you had to guess, what do you think it would be? Endothermic or exothermic?
Exo.
Endo?
So endo, we got votes for both.
Huh.
When you typically do a combustion reaction, is it an exothermic or endothermic reaction when you do combustion?
Exothermic?
So
Pretty much, right? When you burn anything, it's an exothermic reaction. And so if it's an exothermic reaction in reverse, what's it going to be?
Endo.
yeah.
Endo. It'll be the opposite. That's right.
Mm,
All right. So let's look for our reactants and our products. So reaction number 2 gives us our acetylene, but it's a reactant rather than a product. And reaction number 3 has water as a reactant, so that looks like that's on the right side. And number 4 gives us oxygen as a reactant, so we're probably going to have to flip that one around. So what do you think? Who wants to take a stab at this one? What should our first step be?
I think we have to do something with the second reaction. I think we have to reverse it.
Okay, let's do that. So we've got C2H6 goes to C2H2 plus 2H2. Now what's going to be the heat? What's going to be the enthalpy of that reaction?
It'll be positive 94.5 kilojoules.
Yeah, you need to flip.
Or you're multiplying times -1.
Either
So
way,
negative
yeah,
is positive.
you just, exactly. So what else? Do we need to flip anything else?
Reaction 3, the last reaction.
The last one, yeah, it looks like we're gonna have to change that one too. Let's do that. So 2CO2, and since these are all gases, I'm not bothering to write down the phases, gas, liquid, or solid, but you will have ones where one of the reactions will be changing, a gas to a solid, or a solid to a liquid, or a liquid to a gas. And that's a physical reaction, but it's still a reaction, and you need to take that into account. So the last one is 2CO2 plus 3 waters give us C2H6 plus 7/2 O2. So what's going to be the delta H on that one?
Just a positive version of that -283.
Okay,
So it's just 283.
283. Okay. And so what about, so the only one we haven't taken into consideration is the third reaction. And it looks like we can just leave it as it is, right? Because it gives us water which we want. And let's basically this is sort of like an approach I kind of like to take. I mean, just the first thing I do is just get all the reactants and all the products on the right side. Then we can start like trying to figure out whether to divide them or multiply them or whatever. When we get everything on the right side, it's a good place to start. So this will just give us an idea of whether we're okay. So delta H for this will not change. So that is plus 71.2. All right, now let's see if we can actually add this thing together. So if we add, so what's the first thing basically we want to look for things that are in common as reactants and products, and then we can get rid of those. So is there anything we can get rid of?
C2H. Yeah, I agree.
So C2H6 can go. Yeah. Okay. Anything else? Is there anything else we have on both sides that we can get rid of?
By the looks of it, probably not. I think we that's the only thing that we canceled out.
Yeah, I don't
Right.
see anything else.
Right,
Yeah.
so I'm starting to see a problem here because we have 3 waters plus 1. We've got 4 waters as reactants, and we only want 1. So that's a problem.
So do we?
And we've
do we have a
got
form?
3 hydrogens as products, and basically you don't want any. So what do you how are we going to address that problem? We don't want to do anything to the second reaction, the first or the second reaction, because it gets rid of our intermediate C2H6, but we are going to have to do something with this third reaction. So what do you think we should do?
Multiply it by, wait. Oh, wait, no, never mind.
I think we do need to multiply it. We need to do 2 things to it, actually.
I was going to say multiply by 3, but I forgot that it was just hydrogen and not water on the right side.
All right, so we want to get rid of the hydrogens, and we want to
Can
be
we?
1 water.
Oh, never mind.
So what should we do with that last one?
I was gonna multiply it by 2.
Mm-hmm.
Yeah, that makes sense.
Okay, so if we multiply it by 2, 2, 2, and this becomes 1. Now we've got 5 waters as reactants and 4 hydrogens as products. So you were right to multiply it by 2, but what else do we have to do?
And P by 2.
We need to multiply it by 2, and what else?
Flip it.
Flip it, that's
Flip
right. We
it.
need to flip it. We need to flip it the other way. So we need to have 2H2 plus O2 gives us 2 moles of water. So what do we, so we'll get rid of this. So we'll flip it and we'll multiply it by 2. So what do we have to do with this heat of that initial reaction?
Change it to negative and multiply it by 2.
Divide by 2.
Multiply it by 2 because we
Oh,
multiply
really?
the reaction by 2. So we need to multiply the heat by 2 by minus 2 because we reversed it. So that's my minus, and we multiplied it by 2. So we need to multiply it by 2 and reverse the sign. So my new delta H should be minus 142.4, right? That's 71.2 times 2, hopefully.
Yeah.
So just to sort of clean this up a little bit, I'm just going to erase this one. So we just add them together. See if it works out. Okay. So we get rid of our C2H6, so we're good there. What about hydrogen? We've got hydrogen on both sides. Can we eliminate that?
Yeah.
So I got 2 moles of hydrogen as a product in reaction. So let's put them as A, B, and C. So I've got 2 moles of hydrogen as a product in reaction A. I got 2 moles of hydrogen as a product in reaction A. I've got 2 moles of hydrogen as a reactant in reaction C. So I can eliminate those. What else can I start to eliminate?
For reaction C, the
Mhm.
2 moles of water disappear. And then for reaction B, you're left with just 1 mole of water.
Right. So this is gone and I'm left with 1. So I got 1 mole of water here. And what about my oxygens? I have
For oxygen, for reaction
too.
C, the oxygen disappears. And then for reaction B, it becomes 5/2.
Yep. So now let's add them all together. So I've got the only thing left as a reactant is 2 carbon dioxides plus 1 water, which is the same as my target. And what I have left on the right side as reactants is C2H2 and 2.5 moles of oxygen, and everything else is eliminated. And that's what I have up here. So what is the final delta H of the target reaction?
I got 235.1 kilojoules.
Let me double check on that one. 94.5 plus 283 minus 142.4, 235.1. Yep. So just as we suspected, that is an endothermic reaction, and that makes perfect sense because it's the opposite of a combustion reaction, and so it's going to be positive. So this first reaction plus 235 kilojoules. Excuse me. All right, is that clear to everybody?
Mm-hmm.
You guys are doing a
Yeah.
really good job on these. All right, cool. All right, let's go to, is there any one in particular you want to do? Let's do like one more, since you guys are crushing these.
We do number 8.
We'll do one more and then we'll go to 8. Yeah. So just let me know if there's any one of those, like 3, 4, 5, 6, or 7, and then I'll show you 8. Any of them look particularly tricky or anything?
Six.
Yeah, I would agree. 6 looks a little difficult.
6 looks nasty. Okay. All right. So this is oxidation of nitrogen to make nitrogen dioxide. So we want to get to the top. We want to get this reaction right here. Oh dear, that's a little thick. Huh? All right. We want to get to this. So, as usual, I want to find my reactants and I want to find my products. Get them on the right side. So let's just start with nitrogen. From the second reaction, it's pretty clear that I got my nitrogen right there and I got the right amount of it. So I should probably just write that one out and just leave it for now. I think everything's a gas. Yeah, everything's a gas. Right, so I won't do anything with that one. What about the oxygen? Where's our oxygen going to come from?
Our last reaction, it's on the product side, so we could flip that over.
Right, so it seems like that's the only place we're getting oxygen. So we're going to have to flip that one. That's the formation of water. So, okay, and NO2. Where's NO2 coming from?
Third reaction.
Third one, yeah. And it looks like the right amount. So we'll keep that the way it is for right now. All right, so some things looking like there's going to be some issues. So we have the right amount of nitrogen. So we have the right amount of product, but we don't have enough oxygen, and we have too much hydrogen. We shouldn't have any hydrogen left over. So what should be some things to? And water. We should get rid of our water as well. So it looks like we've got some things to do with that second reaction, it looks like. Anyone have any suggestions?
I was going to say that multiplying the last reaction by multiply the last reaction by 4, but the only problem I see with it is that when I do that, the hydrogen will have the hydrogen will become 4 moles, and we'll eventually be left with an extra mole of hydrogen.
Okay, well, let's do that. So that's the oxygen plus hydrogen. That's the water formation reaction, right?
Yeah.
So let's multiply that by 4. So that will be 2 moles of oxygen, right?
Yeah, that'll become 2 moles of oxygen.
This becomes 4, and this
moles
becomes 4. So what do we do with the heat with that one?
Multiplied by 4.
Oh, and what else? So this reaction right here, we multiplied it by 4, but what else did we do?
We flipped it.
Change the sign.
Yeah, that's right. We changed the sign. We flipped it. So we have to multiply that by -4. -4. There we go. So what's our delta H now? So it's 174.8 kilojoules. Positive or negative?
Positive.
Positive. I think there's a mistake here, because that should be negative. The formation of water should be. And well, we'll finish this out, but I think that's a mistake. I'll go back and check on it. But according to this should be positive. I think that's wrong, but so I'm thinking this is wrong. This number here should be positive, because whenever you when you split water into hydrogen and oxygen, that takes energy. So Actually, I might as well just fix it now. I'm sure that's a mistake.
So originally it was positive. So therefore, when we switch,
It should be positive. So this, yeah, this should be negative.
Okay.
I'm going to do that. That should be, oops, that should be negative. Okay, so let's look and let's start adding these things together. See if it works out. So how much nitrogen do I have as reactants?
1 mole of nitrogen.
Just have one, right?
Yeah.
Okay. And how much hydrogen?
7. Yeah, 7.
7, okay. And how much water?
4 on the reactant side.
Mm-hmm. And how much ammonia? Remember what ammonia is?
Oh, 2.
Yeah, and H3. And then what's on the product side? I've got 2 ammonias. I've got 4 waters. And I've got 2 NO2. And I've got 7 hydrogens. So what can so I've got 7 hydrogens on both sides. I can get rid of that. I got 4 waters on both sides. I can get rid of that. I got 2 ammonias on both sides. I can get rid of that. So what I'm left with is, oh, wait a minute, we forgot the oxygens over here. Oops. 2O2. So what's left over is oh dear. What's left over is 2 oxygens plus 1 nitrogen. Everything else is canceled. And my product is 2 NO2. And that is what we've got. Oh man. It doesn't want to draw up there. That's our first reaction. So 2 oxygens plus 1 nitrogen makes 2 nitric oxides. So we've got it balanced. Question is, what are my heats? We figured out what the heat is for this reaction. What about the other 2? What's the heat of this reaction? The first one. What's delta H for this first reaction?
Negative 115.
Right, we haven't done anything to it. So it's the same, it's exactly the same. So it's minus 115. And what about this third reaction? This one down here. This one.
So originally it was positive, so it would be a negative after switching the sign.
We didn't though. We didn't flip it. It's exactly the same.
We didn't do anything to it, did we?
We didn't do anything to that
wait,
one.
wait, okay, wait. I'm sorry, I'm getting, okay, you're right. I'm getting mixed up.
Oh yeah, well I mixed you up by saying the last one versus, I meant this one.
Yeah.
Yeah, I meant this one here. Yeah, we
Yeah, okay, all right. Yeah, we didn't do anything
Whoops.
to it.
Didn't do anything to that. Come on, there we go. And so, yeah, so we should have the same heat, which will be minus 142.5.
Still negative?
Yeah, we didn't do anything to it. So it's minus 142.5 up here, so it should be the same. That has not changed. So now all we need to do is add up this plus this plus this. Add them all together. And that will give us the heat for this last reaction, which is all of them. This last one at the bottom is all of them added together. What do people get?
Negative 432.3 kilojoules.
That is correct. Good job. Yes, I hope you see the pattern of sort of dealing with these. If you find a system and sort of stick with it, it helps these become not so onerous. And so the system I like to use is, find my products, find my reactants, get them on the right side. So I do my flips first. So but sometimes it's going to be tricky if you've got them on both sides. If you like, here we've got water on both sides, but water isn't in our original reaction. So make that the priorities, finding where the reactants are, where the products are, getting them on the right side. Once you've done that, then you can start doing your multiplication. I think that's probably easier than trying to multiply them first and then start flipping them. Okay? But yeah, good job so far, everyone. Everyone's doing a really good job. So why don't I go to the last one? What I'll do is I just want to just briefly go to part of the lecture that we sort of missed out on, because without it, it'll be a confusing question. So let's see if I can.
What was the final answer? Minus 43.
Minus 432.3 kilojoules.
Okay, thank you so much.
All right, so I'm going to share a different screen. All right. Now this is dealing with what we call a phase change. The last question is about phase changes. And the question is, if we start with a block of ice, which would be down here, we start with a block of ice, and we start adding heat to it, how much heat is it going to take to turn it into water vapor? Okay. So this is what the phase change diagram for water would look like. So you can see that there's places where the temperature doesn't change, which is right here and right here. And there are phases of the diagram or places on the diagram where the temperature does go up, here and here. So what happens is that as you add heat to ice, the ice doesn't start to melt immediately, right? Ice doesn't melt until it gets to what temperature? What temperature does ice need to get to before it starts melting? Zero, right. So if I have ice at really cold, if I have it in a deep freeze, like minus 50 degrees or something like that, I take it out of there and put it on a table, it's not going to start melting immediately, is it? It's just going to stay ice until it gets to 0 degrees. And so, but it's going to warm up. It's going to go from minus 50 up to 0. And then it's going to start changing its phase from a solid to a liquid. And that is the second part here. So that is the second part of the phase change right here. When it's going from a solid to a liquid. So at this point, notice that the temperature doesn't change. Why is that? What's happening there? Anyone tell me what's happening at that particular place of the diagram? B and C. From point B to point C, what's actually occurring?
Is it because the heat that it absorbs is going to break the bond? So the temperature
Which bonds? Which bonds? What bonds is it breaking?
H2O.
Nope.
Hydrogen bond.
Ah, there you go. Yes, there are some hydrogen bonds breaking. So there's not chemical bonds, and we're going to get into this, the chapter after gas laws. There are some interactions between water molecules in the solid phase that are different from the interactions in the liquid phase. That's why one's a liquid, one's a solid. And so and those bonds are being broken, and it takes heat, it takes energy to do that. But so what's happening is that heat is going into breaking those interactions between solid water molecules and turning them into liquid water molecules with slightly different interactions. But what it's not doing is changing the temperature, because you know that if you've had like a glass of ice water, it's 0 degree. If you put a thermometer in it, if you fill a glass with ice, then put a little bit of water in it and check the temperature, it's going to be 0. You come back to it like half an hour later and half the ice melted, what's the temperature going to be? If half the ice in your ice water is melted, what's going to be the new temperature?
If it is not completely melt, it's still 0.
That's correct. That's right. And it's going to stay 0 until all the ice is gone. And then once all the ice is gone, the temperature of the water starts going up. And that's what's happening between C and D. So once all of the solid water is turned to liquid, now I have nothing but liquid water, and I start adding more and more heat to it. Now the temperature starts to go up. And this part of from C to D, this part of the heating curve is dependent on the specific heat capacity of water, which we know is 4.182 joules per gram Kelvin. That's what this line is. That's our heating line for heating up water and a changing temperature. So that's dependent on the heat capacity of water. But once we get to 100 degrees, what happens? What's happening at 100 degrees?
Same situation as B and C.
Right. So it's not a liquid, it's not completely a liquid, and it's not completely a vapor. It's both. And so it's changing state from liquid to vapor. And so all of this heat, and you can see that's a lot of heat we're adding from here, from D all the way over to E. That's a lot of heat we're adding. But the temperature doesn't go up. Why is that? Where's that heat? Where's that heat going? What's the heat being used to do?
Changing the liquid to gas.
That's right. It's changing the liquid to a gas. And so just like if you put a pot of water on the stove and you heat it up till it's boiling, the temperature of the boiling water does not change.
Yeah, it gets to like a certain point and then it stops. Right?
Yeah, it gets to 100 and it stops. It can't get any hotter because basically what happens when the liquid turns to a gas is that the vapor is then going into atmospheric pressure, changing the pressure of the water vapor to atmospheric pressure. And the only thing that could make it any hotter is if you didn't allow the water vapor to escape. And so then you could heat the water to a much higher temperature. But as long as it's at 1 atmosphere, it can't get any hotter than that. And if you're up in Denver, for instance, if you're up at a mile high, the water will boil at around 93 or 92 degrees. And so whatever the atmospheric pressure is, that's what your pressure of water vapor is going to be. So all of this, so between B and C, the temperature doesn't change because it's going from a solid to a liquid. And from D to E, temperature doesn't change because it's going from liquid to a vapor. And so what's happening there are, we call those phase changes. So from a solid to a liquid is melting. From a liquid to a gas is vaporization. And just let me go here. So to calculate these things, we need a couple bits of information. And one is how much heat does it take to melt or freeze water, and how much heat does it take to boil or condense water. Now this is different from the heat capacity of the water. Because remember, the heat capacity of the water is how much it takes to go from a cool liquid to a hot liquid. This is different. We're actually changing the state of it. And so have a look here, and you can see that what we're calling, instead of heat capacity, we're calling this the heat of fusion, because it's actually fusing a liquid into a solid. And notice it's 334 joules per gram. Why isn't there, now with heat capacity is joules per gram per Kelvin. Why isn't there per Kelvin here?
Because there is no difference in temperature.
Exactly right. Yeah, the temperature doesn't change. Very good. Yeah, the temperature doesn't change. This occurs at 0 or 273 Kelvin. That's the only place this is the only temperature that this takes place is at 0. So the heat of fusion is how much energy is given off when liquid water at 0 becomes solid water at 0. And it's this much energy. Okay, so that much energy comes out when it's freezing, or you need to put in to get it to melt. Okay, so that's the heat of fusion. Now next is the change from liquid to a gas, or from a gas back to a liquid. And that's called the heat of vaporization. Which makes sense, right? It's vaporizing. So to figure this out, figure out how much heat this is, we just multiply the mass times this heat of vaporization. And you can see it's much higher, because it takes a lot more energy to boil something than it takes to melt something. It takes about 8 times as much energy. And so in order to take 1 gram of liquid water and change that into a gas, you need to add 2,260 joules, okay? Now that is at 100 degrees C. And so the question on your number 8, let me get out of here, come back. So this question here is, you need to do 3 things. So I've got 200 grams of H2O solid, and it's at 0 degrees C. So I need to do 3 things. I need to take my 200 grams of water, and I need to change that to 200 grams of liquid water. Then I need to take my liquid water at 0 degrees and make it liquid water at 100 degrees. Then I need to take my liquid, I need to take my liquid water at 100 degrees and change it to water vapor at 100 degrees. Those are the 3 steps it takes. Take 200 grams of solid water, ice, from 0 and turn it into water vapor. And then these are the 3 bits of information you need to get there. So you guys think you know how you would do that? Who wants to take a guess? What would be the first step?
The first step is to find the amount of heat that it takes to melt.
Right, exactly, very good. And you're crushing this one today. Yeah, first thing I need to do is melt it. So what's my equation to figure out how to calculate how much it takes to melt? What bit of this, which one of these 3 bits of information do I use for that?
The second one,
Second one,
take it multiply with mass.
Yeah, so I got 200 grams. And my heat of fusion is 334 joules per gram. That is the amount of energy required to convert my liquid, my water as a solid and turn it into a liquid. That's how much it takes for it to melt. So that's A.
So you're calculating the energy though, right? Because the grams cancel out.
That's right. Yeah, it's all energy because it's calculate the amount of energy. That's the actual question. So that's why, yeah, you should be real careful with these. Always include the units, because if you don't include the units, you're going to make a mistake. And so, yes, so A is my melting. You need the heat of fusion. What's the second thing I need to do? So after adding some heat, I now have liquid water at 0 degrees. What's the second thing? What's the second part of this process? Now remember, I've got to boil this ice. So my first step, I melt it. So now I've got 200 grams of liquid water and I've got it at 0. What's the next thing I need to do to get it to boil?
To find the amount of heat energy that it takes to increase from 1 degree to from 0 to 100 degree.
Exactly. Excellent. So I've got my 200 grams and I need to go from, my delta T needs to be from 0 to 100, right? I need to change my temperature by 100 degrees. I might as well just erase. I need a 100-degree change in temperature. Either Kelvin, 100 Kelvin, or 100 degrees C. Makes no difference because it's a change in temperature. What do I multiply that by? So I've got my grams. I've got my change in temperature. What do I multiply that by to get the amount of heat it takes to go from 0 to 100?
Heat capacity of water.
Very good. Yeah, exactly right. Yeah, that's my heat capacity. Because remember, the heat capacity just says how much energy does it take to change 1 gram of liquid water, 1 degree C. Now, if I had ice at a lower temperature than 0, let's say if I took the ice out at like minus 20 degrees, like typical freezers like minus 20. I would also need to heat my ice from -20 to 20, from -20 to 0. And to do that, I would need the heat capacity of solid water, which is different than the heat capacity of liquid water, which is also different than the heat capacity of water vapor. Like if I wanted to heat the water vapor to a higher temperature, I could do that, but I would need to figure out how much heat it takes to increase the temperature of water vapor from 100 to higher than 100. So I would need the heat capacity of the solid and the vapor. But here, all I want is how much it's going to take, how much energy it's going to take to change the liquid water from 0 to 100. So that's my second step, moving the liquid water from 0 to 100. And what's my third step? Once I have my liquid water at 100, what do I need to do? So now I've got my 200 grams of liquid water, and it's at 100 degrees already. So what am I doing to my liquid water at 100?
Multiplying by the latent heat of vaporization.
Right, because I'm changing, because that's the amount of heat it takes for a gram of liquid water at 100 to go to a gram of water vapor at 100. So that's 2,260 joules per gram. And you can see that grams cancel out and I'm left with joules. Just the same as with the second part, when I'm increasing the liquid water, my grams cancel, my temperature cancels, and I'm left with joules. And when I'm melting the ice, my grams cancel, and I'm left with joules. But the only thing you have to remember is what sign are these going to be? So when you're boiling something, you're adding heat. And so this latent heat of vaporization will be positive. But if you're going the other way, if you're taking water vapor and it's condensing into a liquid, then your latent heat of vaporization will be negative because you're going the opposite direction. But as long as you have the signs right, basically you just add all these three together, okay?
Just out of curiosity,
Yeah.
are delta T's already known as 100, right? Because you're going from a 0 to 100?
Yep.
Oh, okay, just making sure.
Mm-hmm. Yeah, if you were dealing with something else, if you're dealing with salt water, or if you're dealing with liquid oxygen, or if you're dealing with ammonia or something else, you would need the delta T then would be whatever the boiling point of ammonia is. And the difference between the freezing point of ammonia and the boiling point of ammonia. But since this is water, we know it's 100 degrees. On a test, I may give you something nasty like, actually, I probably will do that. I'll give you ammonia. Or maybe even CO2.
So then after you find your joules, do you add them all up together, and that sum would be the amount of energy required to boil an ice cube to...
Yep.
Okay.
Mm-hmm. Yeah, because it's what most people forget. Yeah, that's a 3-step process. Melting, heating, boiling. It's 3 different things, and it takes 3 different amounts of energy to do them.
And would you say that the key to this problem, or like the concept of this problem, is to follow the phases that water goes through?
Mm-hmm. Yeah, just realize that there's 3 different things happening. Isolate them and figure out what numbers do you need to figure out what's happening. Because the first one is melting. Okay, very first thing I need to do is melt. I don't need to heat the ice because it's already at 0. That's the melting point. So I don't need to worry about the heating the solid water to 0. That's already happened. So all I need is the fusion energy. That's the change from solid to liquid. So I figure that out. Then I've got to go from 0 to 100 with my liquid water. Okay, got to figure out how to do that. but I'm not done because it's the question says I need to boil it. So I need to change the liquid to a vapor. What do I do for that? And then you need the heat of vaporization for that. So yeah, 3 steps, and then you add them all together. I guarantee this will not be the last time you see a question like this. And any other questions?
I was wondering if you could go through number 5.
Okay. Number 5. Okay. So what's your first step in number 5? What do you want to do first?
So when I was doing number 5, I switched the second reaction. So I switched the second I switched the second reaction.
You reversed it.
Oh yeah,
Okay.
sorry, reversed it.
Okay.
And therefore the delta H was going to be a positive number now instead of a negative.
H2O gives us. Man, what's wrong with this thing? Ah! Oops, number 5. C. Man, I'm having issues here. All right. C2H6O plus 3. Okay. Right, so this becomes positive.
Mm-hmm.
So what else did you do?
So after I reversed the second reaction, I realized that I have all the targeted chemicals or mixtures in the right area. Then I multiplied both the second reaction and the third reaction by 2.
Okay. So this becomes, oh, don't want subtitles. What's going on?
Oh wow, you could do subtitles. That's so weird.
Yeah, there's a lot going on here. So this
Wow.
becomes 4. This becomes 6, 2, and 6 here as well. Okay.
And then the last reaction,
Oh,
you would
multiply that
also
as well.
multiply. Yeah, you multiply that by 2. So therefore, you have the 2 moles of the C2H4O on the left side and 2 moles of C2H6O on the right side. That's what I did. That's what I. Yeah, that's what I did to at least get those already in place. The only problem is that after I multiply both the reactions by 2, I started canceling out, like I could cancel out the 4 moles of carbon dioxide. And eventually when you cancel out the oxygen on the right side, you're left with just 2 moles of water on the left side, but I just don't know how to cancel out the oxygen.
Well, you don't have to cancel out the oxygen because there's 5, you want 1 left to be left over. So there's 5 oxygens as reactants here. There's 6 oxygens as products here, and that's what you want. So this goes away, and this becomes 1.
I just realized what I did wrong. I did my math wrong.
Yes, you had the right idea. You just forgot that there was an oxygen left over.
Okay. All right. Yeah, I just did my math wrong.
Okay. All right. Any other questions?
What was that on the right? You had 4 CO2 plus 6 H2O goes to 2 C2H6O, and then what's that? What was the thing you scribbled out?
Oh, I crossed out 5 oxygens because there's 5 oxygens as reactants and 6 oxygens as products. And so net would be 1 oxygen as a as a product.
Oh, okay. I thought, yeah. Okay.
And that's what you want. Yeah, so the CO2s cancel. There's 6 waters on the left side. There's 4 waters on the right side. So there's a net of 2 on the left side, which is what you want.
Right. Okay.
Yeah, so that all works out. Yeah, just make sure that you follow the sign. So you flipped the second reaction, so make sure you change the sign and then multiply it by 2, and then you should be fine. Yeah, this thing does a pretty good job of. Can everyone see the
Subtitles.
at the bottom?
Yeah.
Yeah.
I was realizing it that like it's recording your voice pretty accurately and like.
Yeah, it is.
time too.
I'm impressed.
It really does record.
Yeah.
Try
I'll have to try that.
twisting.
I'll have to try that when I'm writing. Yeah. Or when you're using really complicated chemistry, it might get confused.
Oh yeah, by the way, this is kind of off-topic question, Mr. LeBlanc, but like
Yeah.
your last name, right? Is it Le and then or L-E space and then Blanc, or is it just LeBlanc?
It's just what, yeah. It's there's no space, but there is a capital B.
Oh, okay, got it. All right.
Yeah, I do get a little miffed about that.
Okay. Because I was just on the free time that I have, I usually watch like Friends. Of course
Matt
there's, like,
LeBlanc. Yeah, he has a
yeah.
capital B as well. So yeah,
Yeah, but he has a space in between the L, the E and the L, the E and the B.
he shouldn't.
Oh, okay, well, I
I
guess
mean,
there's many different ways.
Yeah, I mean, I'm pretty sure, I'm sure he doesn't, but that's probably NBC that's responsible for that.
Oh, wow.
Anyway, so if any other questions before we call it an afternoon? I need to get outside. It's beautiful outside today.
Is it
Yeah, you
kind of
gotta take
hot right now?
advantage of it. It's not that hot. It's maybe like
like-
average. Maybe a little bit
I'm
higher.
like sweating in my room. Not. I mean, that's too much information, but like it's.
What?
Thanks for sharing.
I'm baking in my room. Like that's how it feels like. I'm baking.
Oy. Yeah, get outdoors.
Step outside for a little bit.
Yeah, it's perfect
I
out.
don't know. Is it hot? I guess not. Okay.
Like 70 degrees outside.
Yeah, it's a little average. For summer, I mean spring / into summer.
All right. Well, I'm gonna go walk my doggies, and I will. If
Um,
anyone has any questions, yeah, you can email me, send me a message on Canvas. I've been trying to do a good job of responding to everybody.
I have a quick question now.
Yes.
Like for number 6, I didn't get the same answer as you.
Okay. I could be wrong. That's number 6. I can't even remember what we got for number 6. Yeah, just oh, they got rid of all my.
Negative 432.3.
Was that it? Yeah.
Yep.
You got a different answer?
Yeah, so I will have the right answer if I just one sign. Like
Oh yes, it's because this is wrong. That should be positive.
okay, I
Why?
see.
That's why. Yeah, I changed that because that's a mistake. I grabbed some of these questions off the internet, and so when I looked at that, I didn't realize that was a mistake. But yeah, you need to add energy to split water into hydrogen and oxygen. That takes energy to do. So that has to be positive.
Got it. All good then.
Yeah. Any other questions? All right, everyone. I will see you on Thursday if I don't see you sooner, okay?
All right. Thanks
Alright.
again.
Have a nice
All
day.
right. Thanks, guys. You guys too. Yeah, stay well. Stay sane.
Trying every day.
Bye-bye.
Bye.
Bye.